find them, but how to add or subtract from
Actually, resolution is an entirely different thing.
magnitude.
Resolution is not addition of vectors.
That's not.
Resolution means breaking down vectors into its components. Breaking down vector into components, meaning the perpendicular components of a vector. Okay, so basically if you have a vector, this is the vector that you have at a particular angle with the horizontal. This is our horizontal ground. Okay, and this is your angle. Sorry, this is your vector. The white arrow over here represents your vector. And this vector is at an angle theta to the horizontal. And the value of the vector is, let's say, f. The magnitude of the vector is f. Now, remember one thing, the vector can be divided into two components, two perpendicular components. These are called the rectangular components of a vector, okay? And you'll get in a while why it is called rectangular. Rectangular components of a vector. Okay, so basically, there are two components, and first one is the horizontal component, which is right adjacent to the angle theta and right parallel to the horizontal ground. Okay, and this component, it can be calculated using the trigonometric ratios, whereas there is another component which is right perpendicular to this component, and when you add these two components together by using the head to tail method, you get the resultant vector. The resultant is the vector itself. These two vectors are at an angle of 90 degrees to one another. If you want to calculate the value of this horizontal vector, the value is f times cos of theta. Whereas if you want to calculate the value of the vertical vector, the vertical component of this vector, it's f sine of theta. Okay?
Okay.
So if you are, this is how you resolve a vector into its triangular components. Why is it, sorry, into its rectangular components. Why are they called rectangular components? Well, because these components, if they are made from the other side of the vector, for example, if the red component is shifted over here to the tail end of this white vector, and this purple vector is shifted upwards over here, then it makes a triangle. Okay, so sorry, it makes a rectangle. So that's why they are called rectangular components of a vector. So this is the resolution of a vector. And by the way, how did resolution of the vector, and by the way, how did we get the f sine of theta and f cos of theta? We got it using trigonometric ratios. Okay, you can use trigonometric ratios to calculate them. So for instance, and by the way, the derivation has been discussed in the previous class. If you remember, we use the SOHCAHTOA rule. So sine is equal to opposite upon adjacent. SOHCAH, cos is equals to, opposite upon hypotenuse. Cos is equals to adjacent upon hypotenuse, and tan is equals to opposite upon adjacent. Remember, these are the three trigonometric ratios. We can use them to get these expressions of the vector. Is this clear?
Yep.
Okay. Now, if I give you a vector of 10 Newton and I ask you, it is at an angle of 25 degrees to the horizontal, 30 degrees to the horizontal, and I ask you to calculate the vertical component of this vector. Can you do that?
F sine theta, F sine 30, 10 sine 30.
Yes, correct. And the horizontal component?
10 cos 30.
Cos of 30. Great. So you're getting this one. Okay, so this was the resolution of vectors. Now after this, we did the vector addition, right? So if you have two vectors and they are, okay, this is a body over here. And on this particular body, there is a vector acting to the right-hand side of 10 Newton. And there's another vector acting to the left-hand side of 2 Newton. What's the resultant force acting on this body? What's the resultant of these two vectors? Remember, the two vectors are opposite
10
direction.
minus 2.
Yep, 10 minus 2. Because
3,
whenever,
8.
8. Because these two vectors, whenever the vectors are anti-parallel, you just subtract them, get the resultant. Okay, now if these two vectors were parallel to one another and they were in the same direction, 2 Newton is over
We
here
would add
instead of
them.
here. Yep, you add them. Okay, now what if these two vectors are at an angle to one another? This is 10 Newton acting to the right hand side, and there's another vector,
Then we separate the components and then
5
rearrange
newtons.
them.
Okay, we can split the components and rearrange them. What else can we do? That's another method. We didn't do the,
And we find out the magnitude.
yeah, the magnitude of what? What is the name of the rule that we apply over here?
Vector resolution.
No, it's called the head to tail method of vector addition. Remember?
I said to tailor method.
Yeah, head to tail rule basically is used. So what to do first? Pick any one of these
Oh,
two vectors, right?
yes.
So I'll take the 10 Newton vectors. Then what else to do after this? Head and tail.
Oh,
Focus on the wording.
yeah.
Okay.
Well, we place the 5N force horizontally.
No, we basically
Upward.
take the 5 Newton force and put its tail on the head of the 10 Newton force.
Yeah, that's what I meant.
You said we put it horizontally. Putting it horizontally would mean putting it this way, which is wrong. That would change the vector, okay?
Well,
Because
I
this,
meant to put it on the line you just drew, the green one.
yeah, okay, put it on the line, but put what? Put the tail of that vector, okay? You have to be very
Right.
specific.
Yeah.
Put the tail of that vector. Okay, now once you've done this, what's the angle? This angle has been given to you, okay? Remember that. The angle which is below the white line is given to you, not the other side, not this angle. So now,
Okay, yeah.
okay, for instance, if the value of this angle is, let's say, 30 degrees, now how are you gonna get the resultant of these two vectors? Okay, what was the
Oh,
rule of
we add another vector starting from the first of that. Yeah,
starting from the tail of the first vector?
to the head of 5N.
All right, great. You've made me happy. You're getting it finally. Great.
Right.
Okay, so this is a 30 degrees angle over here. What to do next?
Then what? Wait, 180 minus theta. Oh
Okay,
wait, no, sorry, so we have to find that
yeah, we
theta.
have to find, no, this theta, the angle of,
Okay, okay, so 180 minus 30.
which is 150 degrees. Okay, now you've drawn a triangle and you need the magnitude of this yellow vector. What to do next? You remember
We
any rule?
use that. Well, what do we call it? Is equals to 5. Oh no, sorry, that's for when another angle is given.
You can use,
Sokator.
no,
No, that's for 90 angle, right? Right.
yeah.
Wait, there's that rule I forgot.
So basically, we are gonna use the cosine rule over here. So the cosine rule, this is the rule over here, a squared minus b squared. C squared equals a squared minus b squared. It's, wait, c is equals to a squared minus b squared plus 2ab cos of angle c. It's not minus, it's plus 2ab, okay? This is plus
Okay.
2ab cos of angle c. So let's try calculating this. And this is c squared, okay? This is c squared, not just c, it's c squared.
Okay.
Yeah, so then just take square root of the other side and you'll get the value for c. Can you please plug this into the calculator? 10
Yeah.
squared
Okay.
minus 5 squared plus 2 times 10 into 5 times cos of angle c is 150 degrees, and make sure your calculator is in the degree mode.
Okay.
And this turns out to be, there has been an error, just a sec. Basically, this isn't the correct formula for the cosine rule. There's been
Right.
shifting of the signs. This is a squared plus b squared minus 2ab. Now if you plug these values, it's gonna give you the correct answer. Okay, please
Okay.
fix this cosine rule over here. C squared equals a squared plus b squared minus 2ab cos of angle c. Yeah, that's the rule. And then once you do this, take square root of it, okay? It's 14.5, which I calculated.
To take the measurements from a ruler and then take the scale of it.
Yes, okay, so
Then cross
basically,
multiply. If 10 is equals to 2 centimeters, then 5 will be equal to, wait.
that's gonna be too
Wait,
small.
yeah.
Let's assume 2 centimeters is, sorry, not 2. 1 Newton is, oh wait, 2 Newton is represented by 1 centimeters, okay? So
Okay.
this means that we'll need
10 newtons will be x and then cross multiply.
for the, yeah, exactly. So for the 10 Newton, we'll need 5 centimeters using that cross multiply method. And for the 5 Newton, we'll need 2.5 centimeters, correct?
Right.
Okay, so once you got this, you're gonna use your scale. I have the scale. Let me place it. Okay, you're gonna place it the way they have given you, okay? At the right proper angles. Let me make it exactly horizontal. Okay, it's horizontal now. Okay, I'll need the 5 centimeters. So let's say this is the 1 centimeter mark. So let's assume this is the 2, 3, 4, and 5. Let's assume this is a 5 centimeters. So there you go. This is my first vector. After that, for 30 degrees, it should be, the other angle is at 30 degrees to the horizontal. So I'll place it at 30 degrees. For that, you'll need the protractor. Okay, so let me place it at 30 degrees now. Okay, so this is at 30 degrees, and make sure that it's 2.5 centimeters. So I took 1, 2, 3, 4, 5. I took, wait, what did I take on the scale to be 1 centimeter? 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, yeah. Then at 30 degrees, I'll need 2.5 centimeters. It's gonna be 1, 2, and this is a 2.5 centimeters. Okay, after this, I'm just gonna place my scale such that it's from the last vector, from the first vector's tail to the second vector's head. Okay, using the same head to tail method, it's the same, the concept is the same, but over here you just need the scale. Okay, this line has been drawn. Okay, now I just need to measure this line, and according to my measurement, it's 1, 2, 3, 4, 5, 6, 6.5 centimeters, right? Approximately 6.5 centimeters. Okay, it's slightly different from our answer, but it is going to be slightly different because we can't make an accurate drawing, but usually a range is given in the marking scheme for such questions, okay, which they want you to do using scale diagram. Now, just use the scale. 2 Newton represents 1 centimeter, so 6.5 means x, and this x turns out to be 13 centimeters, which is a bit far from 14.5 centimeters. But if I would have used a better scale, I would have gotten a better answer, a more accurate on paper. Okay.
Yeah.
So all you need to know is just the concept and the scale conversion. Okay. The concept is use the head to tail method, draw the diagram, and scale conversion is necessary. And this angle is 150 degrees. Okay. Now, okay. So this was the scale diagram method. Do you want more examples on this, or is this enough on scale?
This is enough.
Okay, this is enough. We can move on then.
Oh, okay.
Coplanar means vectors in the same plane. For instance, the vectors that we've drawn so far, these are coplanar. They are in the same plane as your screen. right? They are as the same plane, in the same plane as your paper. So these are all coplanar vectors. Now, what if you have more than two vectors joining with each other? For instance, this is a vector. Okay, wait.
Oh, so sir, wait, what did you mean again? Coplanar?
Co means same,
Yeah.
and planar means plane. So vectors in the same plane. Plane means surface. Vectors on the
Yep.
same surface. So basically, if you talk about your screen, you assume that the screen of yours is a surface. So this entire screen, the vectors which are in the same plane, which are within the screen, are in the
Oh,
plane.
okay, right.
All right, great. So you got it. Now, what if you have more than one vector acting on the body? For instance, there's a vector acting to the right. More than two vectors actually are acting on the same body. There's a vector acting to the right. There's another vector acting, let's say, upwards over here. There's another vector, let's say, acting somewhere over here. How are you going to get the resultant of these? But it's simple, just add them all using head to tail method, okay? So take any one, let's assume this is the first vector, this is the second, this is the third vector. I place the first vector over here, I pick up the second vector, place it over here. Okay, so let me do it using this method. Okay, I pick this up, I place it over here, right? At the head of the first vector and the tail of the second vector. Okay, the head of the first vector and the tail of the second vector. And then I pick up the third one. And I place it on the head of the second one. Okay, I place its tail on the head of the second one. Once I've done this, I get the three vectors in this pattern. To draw out the resultant, just do the same thing. You start out from the tail of the first vector, go on to the head of the second vector, and you join them. This is your resultant.
Okay.
Right? And if you want to calculate the value of this resultant, well, usually the examiner doesn't ask you to calculate the value. He just asks you to identify what's the resultant is going to be. But if you want to calculate the value of the resultant, it's pretty simple. If you look at this, this is actually a trapezium. So you can use the formulas of trapezium, or you can, instead of using a trapezium, you could first calculate the resultant of the two green, the green and the white vector. You can first calculate their resultant. Of course, some angle will be given to you. This angle, for instance, will be given to you. Okay, these are the two vectors. First, you calculate the resultant of this vector. When you get the resultant of this vector, you pick it up and place it, add it to this vector using head to tail method. Okay, so basically, once you get this resultant using the same cosine rule, you take this resultant from here, you place it over here, somewhere separately, and on the head of this resultant, you place the tail of that vector. Once you do that, you draw out the resultant of these two. Then once you draw out the resultant of these two, let me call it r prime, then you get a triangle. You can use any method which they've given you, meaning the information they've given you. For instance, if they've given you this angle and they've given you this the value of this vector, let's say it's v, then you can again use cosine rule. Or if they've given you another angle in here, for instance, this is beta, then you can use sine rule. Okay? Are you listening?
Okay.
Okay, after this, let's move on. Okay, so in the
Okay.
previous lecture, we did projectile motion as well. So how many motions do we have in projectile? One or two? Is it a two-dimensional or one-dimensional motion? Projectile motion.
Two-dimensional.
Okay, which ones? Can you name them?
Uniformly accelerated motion
Yes, uniformly accelerated motion and
and uniform motion.
yes, correct. And what are their directions?
Um, Uniformly accelerated motions has directions.
Where is it?
Downwards and upwards.
I mean, is it vertical or horizontal?
Oh, horizontal.
It's vertical. Come on.
Oh, sorry, vertical. Sorry.
Yeah, yeah.
Horizontal was in my mind, but called it vertical.
And this one is horizontal, okay? And what's the path, the shape of the path called?
Parabolic.
Okay, it's parabolic. Is it circular?
No, it's not circular, but it's semicircular.
Oh no, it's not even semicircular, it's parabolic. Okay, parabolic is
You
different from
mentioned
circular.
circles, I thought maybe there's something with it.
Now, so since you've correctly identified the name of the shape, you've identified the two types of motions which are involved. Now help me draw out the shape then. Okay, so I'm going correct.
Yep. Oh, no.
Okay,
It goes straight downwards.
it goes up, it goes, it peaks, right? It reaches to a peak.
Yes.
If I stop here,
And then,
this is, if I stop here, this is called half projectile motion, okay? Half
okay.
projectile, because it's half of the full projectile motion. Okay, and if I talk about the maximum velocity over here, what is it equal to?
It's equal to half projectile.
It's equal to which component of the initial velocity? This was the initial velocity with which it was thrown.
Okay.
So is it the horizontal or the vertical component of this velocity which was thrown at an angle of theta?
Horizontal.
Yep, it's horizontal. So how to calculate its magnitude? The horizontal.
It's a V cos theta.
Yep, it's V cos theta, correct. Okay, it's V cos of theta, and it stays constant throughout the motion because the horizontal motion is a uniform motion. And is there any acceleration involved in the horizontal motion?
No.
So what's going to be the horizontal acceleration? It's going to be 0.
Zero.
Right. What about the vertical velocity at the maximum height?
0.
Okay, so the vertical component of velocity at the maximum height is 0. What about the vertical acceleration? Is it 0 or non-zero?
Non-zero.
What is its value?
9.81.
Yep, 9.81 if the experiment is being performed on Earth. And if it's performed on Moon, then it's not 9.81, it's much less.
Right.
It's 1.6, but you don't need to remember this value, okay? It's usually given in the question. Then this is the velocity. Okay, the value of the velocity does not stay constant as you go up. Now, what about this maximum point over here? At this point over here, when the ball has reached, what about the kinetic energy of the ball? Is it maximum or is it minimum at the maximum height?
It's minimum.
Yep, it's minimum. And is it 0 or non-zero?
It's 0. Or
Non-zero.
Non-zero. Non-zero.
Because the horizontal component of velocity is still not 0. Although the vertical component is 0, but the horizontal component of velocity is still there. That's why it's non-zero, okay? This is a common exam question. Now, what if I asked you to calculate this horizontal distance that the ball has covered? How can we do that if the time is given to you for the ball to reach the maximum height? The time for the ball to reach the maximum height is given to you and it's equal to t. How to calculate this horizontal distance
S
that
is
the ball
equals
has?
to ut plus half at square.
Oh no, on the horizontal motion,
Oh.
can you apply the uniformly accelerated motions formula?
S is equal to Vt? No.
Yep, S is equals to Vt is the only formula that you can apply on the horizontal motion. Okay? And the velocity is the horizontal component of velocity. Note this point. The velocity is the horizontal component of velocity in the horizontal motion. Get it? Now,
Yep.
so if I were to ask you to calculate this distance as if the time taken for the ball to reach the maximum height is given to you, the time taken for the ball to reach the maximum height would be the same it would be the same as the time it took for the ball to reach this point, because while the ball was reaching the maximum height, it was also covering this horizontal distance. Both these times are equal, right? You can use that time value to calculate this horizontal distance. And so it turns out to be v cos of theta, which is the horizontal component, multiplied by the time. Calculate the horizontal distance that the ball has traveled. Clear?
Yep.
After this, then if I continue this path and return back to ground, then the projectile is completed. And even while the ball is returning back to ground, the horizontal component of velocity stays constant, v cos of theta, whereas the vertical component of velocity starts increasing as we go down. And I told you that the vertical motion of velocity is analogous to the motion of this ball, which is thrown upwards vertically. It reaches its maximum height, its velocity becomes zero, then it returns back to Earth, and before hitting the Earth, its velocity becomes maximum. This motion is analogous to the vertical motion, to the motion of the vertical component of this velocity, okay? As we go up, the vertical component of velocity decreases. At the maximum height, it becomes zero. Vertical component of velocity becomes zero. And as it returns back to ground, its velocity starts increasing in value. And on the vertical motion, you can use any of those formulas of uniformly accelerated motion. S is equal to ut plus half at squared being the most commonly used formula in the past papers. And then v squared equals u squared plus 2as can be used. Then you can also use s is equals to v plus u upon 2 times t. But remember, in all of these formulas, you have to use the vertical component only. The vertical component of velocity, which is v sine of theta. Okay, not the horizontal component, because the horizontal component is not changing. And there was another formula, v is equals to u plus at. If I were to ask you to calculate
This one, wait, sir, this one would be all this is 2D, right?
all this is two-dimensional, yes.
So it's only going to be uniformly accelerated motion.
In the vertical direction, yes.
Okay.
But in the horizontal direction, no. In the horizontal direction, you told me it's uniform motion. Come on, you can't forget that. Now,
Sorry.
after this, if I were to ask you to calculate the maximum height the ball achieved during this motion, can we calculate that if the time is given to you and the initial, okay, and just the angle is given to you and the velocity is given to you? Can we calculate this maximum height? Think on this for a while. Now, so since you've identified these very correctly, so we use these equations, and the acceleration is non-zero and acceleration is constant. And whenever the velocity is decreasing, acceleration is negative. When the velocity is increasing, acceleration is positive. That's why as you go up, acceleration is going to be negative of 9.81 because velocity is decreasing. The vertical component of velocity is decreasing, and it's becoming zero at the maximum point. So if you're given the time, you're given the you're given the time, and you've calculated this vertical component of velocity, you can get the height. So the height is going to be, you can use this formula. Initial velocity is v sine of theta times the t, which is given to you, plus half times the, instead of the acceleration, you're going to write negative of 9.81 times the t squared. This will give you the height. Right, so this sums up projectile motion as well. And over here. Okay, so basically, if you have a body, a uniform meter rule or a uniform, okay, let's say this is a uniform meter rule, uniform meter rule. So basically, a uniform meter rule is such a rule. Uniform means that it's such a rule that its mass is equal, evenly divided across its length, and its entire force, it appears to act from its center of gravity, right? Appears to act from a center of gravity. Okay, what is center of gravity? Well, center of gravity is an imaginary point on any object where most of the,
Where all the mass acts upon.
yes, where all the mass appears to be concentrated and its entire weight appears to act from that particular point. So if, and for uniform objects, the center of gravity is at the geometrical center. Okay, it's at the geometrical center. So for instance, if the entire length of this plank is 2L, so this center of gravity would be
L.
L from the other side, or it would be exactly at the midpoint from both the sides. Okay, and this is the point
Or we
from
can
where,
place it on a sharp peak to see where it balances.
yes,
That's to check where the center of mass acts upon.
yes, correct. That's an experiment of checking, but that's a very difficult experiment because you don't actually get that very accurately.
Yep.
Uh, okay, and by the way, this is the point from where the weight is acting, because this is the center of gravity, and this weight is acting at exactly half the length of this meter rule.
Right.
That was the concept of uniform objects, and then the center of gravity is the point from where the weight acts. And then we are going to talk about this in a bit more detail when we'll be doing the moments part. But actually, the moments have already been covered. You can watch a very good video on my YouTube channel. It's available there very publicly. The very first lecture. It's
Oh,
for
what's the name?
1 hour, I think. It's physics lectures. You just write physics tuitions. It will come on that by
Okay.
Shafat Khan. The name is Shafat Khan. Okay, the
Okay.
channel name. Okay, so basically there are three Newton's laws of motion. The first law says that any body will stay. Let me write down the statement that any body will continue to move. Will continue to remain in the state of rest or uniform motion in a straight line. Uniform motion means constant velocity, okay? Uniform motion in a straight line until it is acted upon by a force. By an unbalanced force, basically. Unbalanced is usually written in brackets. So if a body is in rest, it will stay in rest. Its velocity will stay zero until you apply a force on it to change its state. And if a body is moving in a straight line at constant velocity without the intervention of any other force, without any frictional force, without any resistive forces, for instance, in space, if a rock is moving at a particular velocity in a particular direction, since there is no other, and assuming that there are no resistive forces, there are no gravitational forces influencing this rock, and there are no other forces in the vacuum in space, then this mass will continue to move in that direction with that particular velocity, okay? Because no force is acting on it. And if you want to change their state, you have to apply a force. This is what Newton's first law was. And if the velocity is constant or velocity is zero, we can say that the acceleration is also zero. Because in both the cases, velocity will continue to stay uh, in that particular value. It will continue to stay either constant at a non-zero value or at a zero value. So this was all about Newton's first law, not very detailed, but just a quick overview of your uh, IGCSE or your O-level stuff. Now, after this comes Newton's second law. That's more important for your AS. Second law. Second law statement says that if any unbalanced force is applied on an object, it will always produce acceleration. This was the definition you did in your O-levels, right? The unbalanced force applied on a body is proportional to the acceleration of that body. And when you
Yep.
replace this proportionality sign, a constant and an equal to come, the constant is the mass. given that mass stays constant. This was Newton's second law that you did. Now in AS, this is a bit more extended. In AS, we define it as, according to Newton's second law, force applied on a body is equal to the rate of change of momentum of that body. Rate of change of momentum of that body. And this is actually the more accurate definition of Newton's second law in terms of momentum. Basically, if you remember what momentum is, what is momentum? A product of mass and velocity of an object is called momentum.
Right.
So force applied on a body is actually equal to the rate of change of momentum of that body. This is Newton's second law. If in the exam you're asked to define what Newton's second law is, this is a definition that you are supposed to write, not the O-level definition. Although that is correct, but in AS this is the requirement, the more advanced definition in terms of momentum. By the way, both of them are exactly the same thing and both of them can give you the same result. But I'm gonna link them in a while. This Newton's second law can be written in mathematical form as well. Newton's second law says that the force is equal to something. It is equal to the rate of change of momentum. What is rate? Rate means anything with respect to time. Change of momentum means there's the change in momentum with respect to time. So force applied on a body is equal to the change in momentum divided by the time. This is called the rate of change of momentum. This is the mathematical format of Newton's second law. And this format can be used to derive this equation as well. The first equation that we used to write in O levels. Now momentum is the product of mass and velocity. If you are asked to define what momentum is, so it is simply the product of mass and velocity. And this definition has also been asked for 1 mark at least. You should know this definition. If it is a product of mass and velocity, then what's the unit of momentum? The unit is going to be kg meters per second. This is a unit of momentum. Kg is the mass, and meters per second is the velocity. That's momentum. The change in momentum can be of 2 types. It can be due to the change in mass, or it can be due to the change in velocity. Usually it's due to the change in velocity. So I can also write it as force is equal to mass multiplied by the change in velocity divided by the time. Right? Change in velocity into mass actually implies change in momentum. Change in velocity means change in momentum, right? Given that mass is constant. Do you agree?
Yep.
Okay. What is change in velocity per unit time? What does this look like? A definition of some other quantity? Change in velocity per unit time is the rate of change of velocity. Do you remember what rate of change of velocity is? What?
Acceleration.
Yes, it's acceleration. So mass stays constant. Change in rate of change of velocity is acceleration. So force is equals to mass into acceleration. You get it? How this formula can be used to get this formula is equal
They
to.
can ask us how this is derived.
Yes, they may ask you. At least they do ask you in Cambridge section.
How do we start it first? Like, because you just showed like 1 step there too.
Yes, you can just show the step. It's gonna be a max 2 or 3 mark definition, derivation.
Okay.
The first mark would be for this point, second mark would be for here, and the third mark would be getting it correctly. Well, you need to show that acceleration is change in rate of change of velocity. You do need to add this point as well. And then this is gonna be the derivation. Here, this is Newton's second law. So more simply, you could just say that any unbalanced force which is applied on a body will produce acceleration of that body. Acceleration can be positive and it can also be negative, which we just saw while we were doing kinematics. It's positive when it leads to an increase in velocity. It's negative when it leads to a decrease in velocity. It's positive when the velocity and acceleration are in the same direction. This is the body. And by the way, before even given that fact, since we know that force and acceleration are proportional to one another, so what's going to be the direction of acceleration? Will it be the same as the direction of force, or will it be different?
Same.
Yep, the direction of acceleration. This is also a very common MCQ. And what is the direction of acceleration? Select the correct statement. So the direction of acceleration is the same as the direction of force.
Okay.
Okay, so now if this is our body over here, it's moving with a velocity v to the right hand side, and if a force is also applied, for instance, by the engine of the body to the right hand side, where would be the direction of acceleration? To the right or to the left?
Right. Right.
Okay, the acceleration due to this force is going to be to the right. The acceleration due to this force is going to be to the right. Is the acceleration in the same direction as the velocity?
Yes.
Okay, so
Because this
since,
is positive.
yep, it's going to be positive. And if it's positive, it will lead to an increase or decrease in velocity.
Increase.
Increase in velocity, correct. And if there were some frictional forces acting on this body, for instance, there was friction acting in the opposite direction, and the acceleration that this friction produced, where would be its direction?
Where the resultant force is acting.
Assume that
Left.
there's no other force. Where will be the direction of acceleration?
Left.
Yep, it's to the left. Now, what will it be positive or will it be negative?
Negative.
Why?
Because the velocity is decreasing.
Yep, the velocity is decreasing, correct. And also because it's in the opposite direction to the velocity.
Yep.
Okay, to which it leads to a decrease in velocity. Okay. Now, if you've got more than one force is acting on a body, there's a forward force, let's call it F. There's a backward frictional force, let's call it small f. Now, if I were to ask you to calculate, and there is a velocity, initial velocity in the forward direction, which is actually of no use to us for now. But this is the mass, and I asked you to calculate the acceleration of the body. Before doing that, I have asked you to apply Newton's second law. What's going to be the Newton's second law in terms of force, mass, and acceleration? How are you going to apply it over here?
F is F minus the resistive force.
F is equal to ma, basically, I'm asking that. Yeah, F minus
So
resistive force,
that would be the resultant force, which we'll add into the F is equals to ma.
which is equal to what?
Resultant force,
Yeah, and resultant force is equal to
ma.
ma. So forward force minus the backward force is equal to ma. This is an equation that is very useful. Okay, this is a Newton's second law equation. And this F minus F is actually the resultant force or the net force. F net equal
And
to,
if the forward force is lesser than the resistive force,
then the acceleration is going to be negative.
okay.
Yeah, because then the resultant that you get is going to be negative. If the resistive force is greater than the forward force, then deceleration would occur and acceleration is going to be negative. Because these two will give you a negative answer, right? In that
Okay.
case. Okay.
And what?
Inclined plane, basically.
Oh, okay, yeah, yes, yes.
Yeah, on an inclined plane, we can apply Newton's second law as well. So basically, if you have an inclined plane, means that this is the horizontal ground. This is your horizontal ground, and there is another, there is a ramp in front of it at an angle to the horizontal, moving upwards. This angle is 35 degrees, but okay, let me decrease the angle a bit, make it 30. Okay, this angle is 30 degrees. Now, on this inclined plane, you can apply Newton's second law, and you can also apply the concept of resolution of vectors. There are actually many concepts that can be applied over here on this inclined plane. Let's try summing all of them up in this lecture. Okay, so if this is a cart or a body moving to the right hand side with a velocity v, the mass of the body is m. The velocity is constant. Okay, as soon as this cart reaches this point and it goes up, and after a certain time it comes to rest, assuming that this this ramp is frictionless. Okay, there is no frictional force acting on this body. Frictional force is 0. Now, can we apply the Newton's second law on it? Let's see. So basically, let's identify all the forces acting on this body. When I ask you all the forces, that means all of them. Okay, all of them. Not even a single one should be left. So the very first
Okay.
force that is acting on it is the weight force downwards, W. By the way, W, the weight of a body, is equal to mg. Right? This is what you know
Yep.
from Newton's second law as well. Where m represents the mass of the body and g represents the gravitational acceleration or the gravitational field strength. Okay, it's also called the gravitational field strength, has a value of 9.81 Newton per kg. Is a unit for gravitational field strength, or if you want to write down the gravitational acceleration, it's meters per second squared. So instead of W, I can just simply write mg, because the mass is m and gravitational acceleration is g. Okay, this mg can split into two components. So before splitting it into two components, identify the other force that's acting on this card. There's one more force. Do you notice that force
Acting
on this card?
on rest. Yep.
Okay, the normal reaction force, you should know the name of it. Okay, the
Yep.
normal reaction force is acting upwards, and it's perpendicular to the surface. It's at 90 degrees to the surface. That's why it's called a normal reaction force. Normal means any line that is perpendicular. Normal reaction force. Now, this card is stationary at this particular point. We need to see the forces that has balanced the normal reaction force. There must be a force that has balanced the normal reaction force. If the normal reaction force is not balanced, then this card should have gone upwards, but it is balanced. So that force is actually a component of this mg. This mg splits itself into two components. This is the horizontal component
And the
and
vertical.
the vertical component, and there is a 90-degree angle in between them. And the angle that is formed over here is the same as the angle of the inclined plane, which in this case is
30.
30 degrees. Okay, this is a fact to remember. These two angles are the same. The reason for that is because these two triangles, these are similar triangles. If you remember what similar triangles were from your math, they
Yep.
have same angles, right? The corresponding angles are the same. Now, if this weight is mg, this yellow force or the yellow vector is mg, this is mg. Okay, let me write it somewhere down here. This is mg. What's going to be the value of this white force?
30 cos. Oh, sorry. F cos 30.
I think mg cos of 30, right? Good, yes, because it's next to the 30 degrees angle. And what about the blue one?
Sine, mg sine 30.
Mg sine of 30. This mg sine of 30, instead of drawing it over here, we can also draw it over here, down the plane. Mg sine of 30. Okay, because its direction is down the plane.
Right.
And now, since it's acting down the plane, by the way, this is also a common question to identify the force which is acting down the plane. So it's mg sine of theta, or the mg sine of 30. And the component which is perpendicular, which is actually balancing the normal reaction force, is mg cos of 30. It's usually the mg sine of 30 that the examiner is more interested in. Now let's look at it. So basically, this mg sine of 30 is acting downwards. When this cart was moving upwards, was this mg sine of 30? Let's assume that the cart is still moving upwards. Okay, let's assume. Let's assume its initial velocity was not v. Let's assume it was coming in with some force acting on in the forward direction. It was accelerating. As soon as it reaches over here, the same force is acting in the forward direction provided by the engine of the cart. And at the same time, mg sine of 30 is acting backwards. And if I ask you to apply Newton's second law on this, can you do that on this cart?
Yeah.
Okay, so what's going to be the equation that you'll get for Newton's second law? Will we get any equation in the vertical direction?
Yes.
What's the equation?
Mg cos 30 and n.
Cos 30 is equal to n, right?
Yeah.
In the vertical direction, they are opposite to each other, and the cart is not going up or down, means there is no acceleration in the vertical direction. So that's the only equation that we can get from the vertical plane. So what about this one, the down the plane? Can we get an equation from here?
Yes.
What's going to be that equation?
Mg sine 30 will be equal to f.
Uh,
Yeah.
no, it's not going to be equal to f. It's going to be equal to f only if this cart was moving at a constant velocity. But I'm telling you, the cart is not moving at a constant velocity. It is moving with some acceleration. The forces are always, whenever the forces are equal, then velocity is either constant or it is zero, and that motion no longer stays as uniformly accelerated motion, but rather it becomes uniform motion. Okay, remember that.
Okay.
And whenever the car is moving with some acceleration, that means that motion and the acceleration is constant given this condition, then that means that the car is moving with a uniformly accelerated motion. So what's going to be the Newton's second law in this direction? What's the concept? What's the formula that you apply? Do you remember any formula from Newton's second law? What is F equal to?
Ma.
Yeah, it's equal to ma. If m is equal to ma, and if I want, what is this F?
It's the resultant force. So to get the resultant force, we subtract the forward force with the backwards force.
Yes, so the forward force is F. This is F net, okay? Forward force is F minus mg sine of theta will give you ma, and this a is the acceleration of the cart. Okay? So F minus mg sine of 30 is equal to ma is the formula that we're gonna apply. This is the Newton's second law in this direction, and basically this is a very, very commonly tested question, especially when you are doing inclined plane. Clear?
Right.
This was all about the inclined plane forces in terms of forces. We also can deal with inclined plane in terms of energies. Okay, Basically, as you go up, it's gaining height, right? Gain in height
Yep.
means which energy is it gaining?
MGH.
Yep, it's gaining mgh. It's gaining gravitational potential energy. Okay. So this is your angle theta. There is a cart moving with a constant velocity forward, has a mass m. It moves up this plane, and after reaching a certain point, it stops at a particular point after gaining a certain height. Let's assume the height is h. And given that this cart, given that this ground is frictionless, what are the energy conversions that have been applied over here? Although it's a frictionless ground, and although there are no frictional forces, but mg sine of theta is still there, which is actually a resistive force. Let's assume that the distance that it traveled in the direction of mg sine of theta is s. So now the total energy that it had initially was a kinetic energy, right? This kinetic energy got converted into two types. First of all, it got converted into potential energy, gravitational potential energy, because it's gaining height. And secondly, it got converted into work done against the resistive forces. Work done against resistive forces. The value for kinetic energy is going to be half mv squared. The value for potential energy is going to be mgh. And the work done against the resistive forces, what's that?
F into D.
F into
Distance. S.
what's the F?
MG sine theta.
Yes, correct. So mg sine of theta, this is the force, the resistive force, multiplied by the s, which is the distance that has been covered. So this is the energy conversions in case when there is no forward force acting and the body has turned to rest. Turning to rest means its kinetic energy has become zero. Now what if there was a forward force still acting on this body? Now let's see. There is another case in which the body is going forward, applying some force forward as it moves on this inclined plane, still applying some force forward, and it covered some distance as a height h, velocity staying constant. Okay, this is a point to note. Velocity staying constant. This is a key point. Initial and final velocities are the same. No frictional forces are acting. Frictional forces are zero.
Okay.
Now, what's going to be the energy conversions for this answer moving from this point to this point, meaning point A to point B? Okay, by the way, just ignore this portion. Assume that we are considering the motion just from this start, okay, of this inclined plane, just from this point A and not from this point.
So we're calculating the what?
We are just making an equation for the energy conversions.
Okay.
There is a forward force. The distance that it has traveled is s in the forward direction. The angle is theta. Frictional forces are zero. Height is gained is h. The velocity initial and final are the same.
So half mv square is equals to mgh plus the forward force, which is F is equals to ma.
No, basically over
So since
here,
we don't have the resistive force.
resistive force is present, but the frictional force is zero. Doesn't the cart have weight?
Right.
It does have weight, right? So it's mg sine of theta. It's still there. It's always gonna be there as long as the body has weight. Keep that in mind.
Okay.
Yes. Now, if mg sine of theta is acting backwards, okay, so basically, first of all, you should know what is the source of energy. The source of energy is actually the work which the body's engine is doing, the work which this forward force is doing. What's the work that the forward force is doing? This is the force provided by the engine. By the engine. It's not some sort of a resistive force. It's not a force that is utilizing energy, but it's rather the force that is the source of energy.
Okay.
So what's the work which is done by the engine?
F into S.
Yep, it's F multiplied by the S. What is it equal to?
Work done.
It is converted into some variety of energies, right? What is the first one? Is it the height? Or it can be the resistive forces? This is the energy that is applied by the engine. This energy is converted into a variety of energies. Okay, it can be converted into gravitational potential energy. It can be converted into work done against resistive forces. And it can also be converted into kinetic energy. Now, what are the energies into which this work has been converted in this scenario? Is there any work converted into gravitational potential energy?
Yes.
Height is gained, right? So
Yes.
yes, whenever height is gained, yes, gravitational potential energy is one of the energies into which the work is converted. What about the resistive forces? Frictional force is zero, but are the resistive forces zero?
No.
They are not. So work is still done against resistive forces. What about the kinetic energy? Now this is a point.
It gets converted to this too.
Why? What
Because
was
as
the?
you gain mgh, you also gain kinetic energy.
No, that's not important. You gain kinetic energy if the velocity is increasing, only then. But if the velocity is staying constant, its initial kinetic energy was also half mv squared, and its final kinetic energy is still half mv squared. So have we done any additional work to increase the kinetic energy if the velocities are constant?
No.
So whenever velocity is constant, no work is converted into KE, kinetic energy, okay?
Okay.
This is a very important point to note. A lot of MCQs are tested using this concept. So whenever an object is moving at a constant speed or constant velocity, that actually means we are not doing any work on it to convert it into kinetic energy. We must have been doing work into some other sources of energies, some other forms of energies, but no work is done to increase the kinetic energy. Okay?
Okay.
So gravitational potential energy is going to be mgh in this case, and the resistive force is going to be mg sine of theta is a resistive force. The distance traveled in that direction is s, this one. And kinetic energy is zero. Change in kinetic energy is zero, right? So this is the equation that we get in terms of energy conversions. And this is an important equation as well. Now there is a third case when the kinetic energy also increases. That is simple to identify. That is the case when this final velocity is greater than the initial velocity. Okay, so the final velocity is, let's say, it's 100 meters per second, and the initial velocity was, let's say, 90 meters per second. There is a change in kinetic energy, right? This means that yes, work has been converted into kinetic energy as well. So in this case, in the case which I've given now, work done is converted into gravitational potential energy. It's converted into against frictional forces. and it's also converted into kinetic energy. Work done is F into S. Gravitational potential energy, assuming that the height is the same, so it's going to be mgh. Frictional force, assuming the mass is the same, frictional force is 0, but resistive forces are there. So mg sine of theta into S. What's going to be the change in kinetic energy? Any idea?
Uh,
What's the formula for kinetic energy?
half mv squared.
So what's going to be the change in kinetic energy?
Half mv squared. Yeah, v1 minus v2.
V1 squared minus V2 squared. This is not the same as V1 minus V2 whole squared, okay? They are not the same. This is a very common error which students make. These two equations are not the same. This one, there is a square outside the brackets on the whole thing. Whereas in the first equation, there is a square on the individual velocities. If you use both of them, they'll give you different answers, okay? And this is the correct one. Get it?
Yep.
Add this over here as well. It's gonna be half m times p squared minus u squared, or v1 squared minus v2 squared. Final minus initial. And if frictional forces are also there, what to do in that case? Well, nothing. Then you just need to add a column for frictional force, sorry, a component of frictional forces as well. So now, let's assume frictional forces are also there. Okay, so now let's try it over here. Horizontal ground, this is again the inclined plane. This is the body going upwards. There's a frictional force F acting backwards. And everything else stays the same. The height is h. The forward force by the engine is F. The distance traveled is S. There is also change in initial velocity was u, final is v. Now, let's make a complete equation. Forward force is F into S is equal to gain in height, which is mgh, plus the work done against frictional forces. The frictional force this time is also F. So F multiplied by the S plus what's the other frictional force acting in the backward direction? Is it mg sine of theta?
Yep.
Resistive force. So mg sine of theta into S plus what else is there? Is there change in kinetic energy as well?
Yep.
Yeah, different.
Half mv1 square minus v2 square.
Or just v squared minus u squared, same thing. Okay. There you go. The entire equation in terms of energy, in terms of forces, the inclined plane, entire chapter has been covered right now. Is it?
Energy over time or work done over time.
If you want to define power, what is power?
Joules per unit
Joules per unit
time.
time. Okay, that's actually a mixture of the,
Rate of work done.
yeah, basically it is the, yeah, rate of doing work or rate of flow of energy. Rate of doing work or rate of doing work or work done per unit time is also correct. Rate of doing work. The joules per second is not the definition of power, but rather it's a definition of a watt, which is the unit of power. Okay, 1 watt is equal to joules per second. Okay, so if you are asked to define what a watt is, 1 watt is, which is joules per second. It's a 1 mark definition that comes. Okay, so now power is the rate of doing work. If I were to ask you to write down equation in terms of power conversions, so all you need to do is just divide all of the components by time. each component by time, and you'll get the entire expression in terms of power.
Also, in momentum, we did not go over the momentum time graphs and inelastic and elastic collision.
Okay,
No, we did in the other class.
momentum time graph. I didn't do that. Okay, I'll do it right now. Don't worry. And I'll discuss that in class as well. By the way, we did, I think I should have covered it, momentum time graph. That's a very important graph. Force is equals to rate of change of momentum. Momentum time graph is actually going to be a direct relationship graph because force will stay constant in that case. Momentum will be proportional to time. If you were to draw it out, it's going to be a straight line passing through the origin, momentum against time, because this is a direct relationship. But I think what you mean to say is the force time graph. This one,
Yes.
force time graph.
Also, power time graph.
Yes, all of this, I'm coming to that, those after this. So basically, if you divide each of these components of the equation by time, you'll get the power conversion equation, okay, the equation of power conversion. And usually the questions of power are such that they just ask you to calculate the rate at which energy is being transferred by the person. For instance, a person is there who goes up a flight of stairs in, let's say, 2 seconds or 3 seconds or 5 seconds or 10 seconds or 15 seconds. Okay, each staircase has a height of 0.1 meter, for instance. There's a boy whose mass is, let's say, 70 kg, and he goes up and the stair over here in, let's say, a time of 5 seconds. So what's the power that he did? What was the rate of flow of energy that he did in this case? So basically, what he did is that he actually gained height, right? So power in this case is actually the change in gravitational potential energy per unit time. Can I say that? Because he's actually gaining gravitational potential energy given that he moved with a constant velocity, okay? No change in speed. Hello?
Yes.
I'm saying that this is a question that usually comes in which a flight of stairs is given to you. The height of an individual step is given to you, 0.1 meter. And then the time is given to you for a person to go up the stairs is, let's say, it's 5 seconds. The height is h, which is, let's say, 5 meters. Okay, not 5 meters. The height is something that you need to calculate because the individual step is given to you. Then you are asked to calculate the power that this boy applied to move from the lowest position from here to the top. So first of all, you need to look at the number of steps which are there. 1, 2, 3, 4, and 5. 5 steps means a total of 0.5 meters. Okay. And then time is 5 seconds. If time is 5 seconds and the height is 0.5 meters, you want to calculate the power. Power is the rate of change of energy, meaning mg,
Yep.
change in height upon time. M is constant, which is 70. G is constant, which is 9.81. Height is, in this case, 0.5, and the time is 5 seconds. This turns out to be 70 into 9.81 into 0.5 divided by 5. 68.67 watts is the work which he has done, or the power that he has done, approximately 69 watts. To want to write it in two significant figures. This is the work of increase, or this is the rate at which the rate of increase of gravitational potential energy of this boy. You get the working? If you have question regarding this working, please ask. Momentum has been used to define force, and momentum is by definition the product of mass and velocity. And if you divide the momentum by time, that becomes the rate of change of momentum, which is actually equal to force according to Newton's second law. Correct? Now, if this is a body moving to the right with a mass of, let's say, 5 kg and with a velocity of, let's say, 5 meters per second, then its momentum is just going to be 25 kg meters per second. This unit can also be written in a different format. It can be written as Newton's second, I think. Yeah, Newton's second. Okay.
Yes.
Do you know how I converted this from kgms minus 1 to Newton second, or the other way around? You know the conversion? Basically, you split it into SI base units. Newton means force into,
Yep.
means force, right? It means mass into acceleration. The unit of mass is kg. Unit of acceleration is meters per second squared. If you multiply that by second, you get kgms minus 1, which is a unit of momentum. Now, if you have this, so momentum divided by time is force. I can also say that momentum is equal to force into time. Okay. Now, if I use this momentum, which is the product of force and time, has a special name and it's called impulse. Okay. The product of force and time is momentum as well, and it's called impulse. You can also get this formula using this unit as well. Newton seconds actually means force and time, right? Force into momentum is equal to force into time. What's going to be the graph of momentum against time? Any idea?
There's
Given that force stays constant, let's assume force is constant. If force is constant, do we have a direct relationship?
yep.
Yes, we do. Because force is constant, right? Force is constant, you can remove that out, you can remove out the equal to sign, and they are proportional to one another. So the graph is going to be a typical direct relationship graph. It's a straight line passing through the origin. Okay. Now this graph can also be different. By the way, the gradient of this graph represents something. What does the gradient of this graph represent? Any idea?
Momentum.
Momentum is represented by the y-axis. Gradient change in momentum over change in time, which is equal to
work done.
Force. Newton's second law. Look at this equation.
Oh.
Yeah, it's force. It's force, okay? It's force. Now, after this, let's assume the constant forces are being applied on that body, right? The same scenario. If the force applied on a body is constant, and if I were to ask you to draw a graph of force against time, what's gonna be the shape of this graph? How is it going to look like?
A curve going from downwards to upwards.
No, force is constant. It has a constant value. It's gonna be constant, right? Are you getting my point? It's gonna be constant because the value of force is not changing. It's staying at F. You get this point?
When does force stay constant?
When it's given to you in the question.
So straight away they say that it's constant?
Yeah. Or they just give you a value that the force of 10 Newton is being applied on an object of this mass. So that actually means that, yeah, constant force of 10 Newton is being applied.
Okay.
Yeah. Okay. Whenever a magnitude is given, then the force is usually constant. Okay. Otherwise, if it's not, they usually state it in the question. Now, well, you will get the scenarios once you start doing more of the past paper questions. You'll find them easier now than after to do the past paper questions. Now, if I were to ask you to calculate the area of this graph, what's going to be the area of this graph? Area under the graph. How to calculate this? Is this a rectangle?
Yes.
This is a
So we can just do height into like length into breadth, which is the vertical and the horizontal
into
values.
force into time, right?
Yep.
What is force into time equal to?
Power. Oh, wait, no. Wait. Yeah, power.
It's momentum. The P is representing momentum in this case.
No.
Yep, it's momentum. Okay, so
I keep
momentum.
reading it as power.
No, it's momentum. Okay, momentum is also represented by the P. So P is equals to force into time, which is momentum is equals to force into
That would
time.
be italic P.
Sorry?
Italic P. Right? Font.
Yeah, it is italic P, but I don't know how to pronounce that italic one. It's not
Yeah, no
this one,
problem.
but it's something else. I don't really remember it. But now this momentum, which is force into time, has a special name and it's called
Impulse. Okay.
impulse. Note this as well. So this is how you calculate the impulse. Impulse, by the way, is actually change in momentum. Okay, it's not a constant value of momentum, but it's rather a change in momentum into, which is equal to force into change in time. If time is changing, right? All the force is constant. If a force is existing, that means that momentum will also be changing, because force by definition means change in momentum. So if you rearrange this formula, change in momentum is equal to force into time. This was the Newton's second law, remember?
Yeah.
This was the Newton's second law. If I were to rearrange this force into time, then it would become change in momentum. Change in momentum is equal to force into time. And this change in momentum is impulse. If you are asked to calculate the impulse, that actually means you are asked to calculate the change in momentum.
Okay.
Following. So law of conservation of momentum says that in a system of interacting bodies, in an isolated system, isolated implies that no external force is acting on it. Okay, in an isolated system of interacting bodies, the total momentum before collision, the word total is important. Okay, this is keyword. Total momentum before collision equals the total momentum after collision. This is actually a 3-mark definition, okay? The word total is important, before, after is important, isolated is important. Clear?
Okay.
And this has been asked that what does the word isolated mean? So isolated means no external force acts on it. If this is a first body, this is a second body. This is U1, this is U2. This is M1, this is M2. They collide with one another after collision. This becomes V1 and this becomes V2. And this is still M1 and that's still M2. And you could apply the same equation. Total momentum before collision is going to be M1 into U1 plus M2 into U2, which is equal to M1 into V1 plus M2 into V2. That's the law of conservation of momentum. And by the way, this U2 and U1 are opposite. If the value of U1 is 10 meters per second, then the value of U2 is, let's say, 20 meters per second, then one of them is going to be taken as negative because their directions are opposite and momentum is a vector quantity. Okay, so no matter what direction you take positive, take right positive or the left positive, it's up to you. But make sure that both of them have opposite signs because of the opposite directions. Even when they are leaving, they must have opposite signs. And the sign of these, the signs in the same direction, meaning if the direction of the body, the direction of the velocity is to the left, then if you assume that the left is the positive one, then both the velocities must have positive signs. And if you assume that the direction to the right is positive, then both the bodies to the right should have positive sign, whereas the other bodies relative to these would have the opposite signs. Do you get this? So now if you have this body over here, there's a mass of 5 kg, it moves to another body, it has a mass of 2 kg. This mass of 2 kg is moving with a speed of 2 meters per second. This is moving with a speed of 4 meters per second. Now let's assume that the speed to the right is positive. So to the right, this force to the right is positive, this must be negative. Now total
Okay.
momentum before collision is gonna be the momentum of this body and the momentum of this body and add them. Momentum of this body to the left, which is, let's assume it's body A, this is body B. So the momentum of body A is gonna be 5 into 4 plus the momentum of body B is going to be 2 into minus 2. This is a total momentum before collision. 5 times 4 is 20, minus 4 is going to be 16 newtons second. This is a total momentum before collision.
Okay.
Total momentum before collision. And what's going to be the total momentum after collision? So for that, you'll still need the values given by the examiner. So the examiner will give you some values. Let's assume the 5 kg body starts moving to the left hand side with a velocity of, let's say, 3 meters per second now, and the 2 kg body starts moving to the right hand side with a velocity of, let's say, mm, also 3 meters per second. Okay, not 3 meters per second. Let's assume it's 2.5 meters per second this time.
Okay.
Now
2.5 is going to be positive, 3 is going to be negative.
3 is going to be negative and this is going to be positive. Yes, correct. And then calculate the total momentum after collision. Well, actually, these are the values that I just made up myself.
Yes.
Let's assume that this is a velocity v that you need to calculate. Now we can do this. Okay, so the total momentum after collision, this v is going to be positive and that's going to be negative. So after collision, it's going
So
to be
minus
2 times v
v into 2.
plus 5 into minus 3, which is minus 15. This is the total momentum after collision.
Yep. So we place the
We equal
16,
them.
16 is equals to this.
We place them equal to each other and then find out the value. The 2v is going to be 16 plus 15, which is 31, and v turns out to be 31 upon 2, which is 15.5 meters per
15.5.
second. And keeping this in mind that if we've got a positive value, this actually means that the direction is to the right. Direction is to the right, okay? Even if you didn't know the
Professor,
direction.
how did you multiply so fast?
How did I apply so fast? Well, I've been doing this since
No,
like
no, no.
4 or 5 years.
Okay.
So that's why. Sorry, not 4 or 5 years. Actually, I've been doing this since my A levels. So I've done tons of past papers as well. So that's why. Plus, I've been solving a lot of queries related to. Okay. Now let's do law momentum in 2 dimension. So basically, this is when momentum occurs in 2 dimension. So basically, for now, we've just assumed that momentum was occurring in the horizontal direction. Now, what if the momentum occurs in the vertical direction in addition to the horizontal direction? So for that, basically, let's take the example of two bodies. This is the first body, and this is your second body over here. The second body is at rest. The white body is at rest. The blue body is moving towards the white body. And as soon as the blue body, which was moving at a velocity, cannot be, was moving at a velocity u. As soon as the body u, velocity, the blue body with a mass m1, white body with a mass of m2, the blue body with a mass of m1 and velocity of u1 comes and collides against this white one. The blue body, it changes its direction and moves upwards at an angle to the horizontal. And this angle, let's
Okay.
assume, is alpha degrees. and the velocity with which it was moving upwards, velocity with which it has been moving upwards is v1. Okay, u1 was its initial velocity and v1 is the final velocity, whereas m2 also changes its path and it also moves at an angle to the horizontal downwards, and the angle at which it moves downwards is beta. Let's assume it's beta. Now we have two types of motions. We've got the horizontal motion following this path, and we've also got vertical motion because these two balls are now going upwards and downwards, right? They're covering vertical height. In this case, how are we going to apply the law of conservation of momentum? Any suggestion? So basically over here, what you're going to do is you're going to look at the momentum in the horizontal and in the vertical direction as well. You're going to apply the law of conservation of momentum in both in the horizontal direction and in the vertical direction individually, and both the horizontal and vertical motion are independent of one another. Now, if you look at the horizontal motion, the initial velocity, okay, what was the total momentum in the horizontal direction initially? But before I move on to the horizontal direction, let me split these vectors into their components. This velocity is v2, okay? The velocity with which this m2, the white ball, is moving downwards. Now, these velocities are given to you, v1 and v2, and these are velocities, so they are vectors. The horizontal component of v1, what's going to be the horizontal component of v1?
Cos.
Cos of what? Alpha or beta?
What were we calculating?
The horizontal component of v1.
So alpha.
It's alpha. And what's the vertical component of v1?
Sine.
And what about v2? Horizontal component of v2?
V cos a beta.
v2 cos of beta, okay?
Okay, V2.
And
yeah.
what's the vertical component of beta?
V2 sine beta.
Right. Now, basically, in the horizontal direction, the initial velocity was u1. The final velocity in the horizontal direction is actually the horizontal component of v1 and the horizontal component of v2. Okay? These are the final velocities in the horizontal direction. So now let's look at the horizontal motion first. Apply the law of conservation of momentum in the horizontal direction first. So in the horizontal direction, basically the total momentum before collision was actually m1 multiplied by u1 plus 0. Why 0? Because initially this body was at rest. This white body was at rest, right? Then what's the final momentum in the horizontal direction? The final momentum in the horizontal direction for these two bodies. In the horizontal direction for the blue one, it's v1 cos of alpha is its horizontal component of velocity, right? So it's going to be v1 cos of alpha multiplied by the mass of this blue body. The mass of blue body is m1. Okay, now added to the horizontal motion of the white body, or the horizontal momentum of the white body, which is gonna be, what's gonna it be? What is it equal to? The horizontal momentum of m2, the white body.
V2 cos B.
v2
beta.
cos of beta multiplied by
Do.
m2. Yep, we are calculating momentum. That's why we have to multiply the mass and velocity, both of them. This is the equation that you get in the horizontal direction. What about the vertical direction? Well, in the vertical direction, these two momenta, they are going to be equal to one another. Or in other words, I can say that the momentum in the upward direction and the momentum in the downward direction, they are equal to one another. Why? Because they are opposite to one another. Initially, was there any momentum in the vertical direction?
What did you say, sir?
I said initially, was there any was there any momentum in the vertical direction?
No.
No. So initially okay, now we are dealing with the vertical motion now. Vertical. So initially, since there was no momentum in the vertical direction, so initial momentum in the vertical direction was 0. Now, what's the final momentum in the vertical direction? Now, for the final momentum, you have to be very careful. Basically, these two velocities are actually vertical, but they are in the opposite direction. So if you assume that the velocity upwards is positive, then you have to assume that the velocity downwards is negative. Okay?
Okay.
So now you just use them in momentum. So V1 sine of alpha, which is positive, multiplied by the mass of this blue body, which is M1, right? The mass of this white body is M2. So mass of blue body is M1. By the way, do not forget to multiply it with the mass, okay? Because we are using momentum. And then
Okay.
add it to the vertical motion of this white body. What's the vertical motion of the white body? Vertical velocity is V2 sine of beta, but with a negative sign,
Okay.
multiplied by the mass of the white body, which is M2, and this is the motion in the vertical direction. By the way, this can be rearranged. This negative sign, when it goes on to the other side, it becomes V1 sine of alpha multiplied by M1 being equal to V2 sine of beta multiplied by the M2. This is the final equation that you'll get in the vertical direction for momentum. Get it?
Yep.
This was momentum in 2 dimensions, and this is very important. Has been tested. It was even tested in 2019.
Okay.
Yep.